Good morning to everyone, and welcome back to the third of this series of lectures. Before starting this lecture, let me very briefly summarize what we did last time. In the last lectures, what we did was to introduce two big classes of interesting examples of Frobenius manifolds. We introduced a class of examples coming from enumerative geometry, from Witten theory. The Frobenius manifolds that arise in that context are called quantum cohomologies. And also another class, a class of Frobenius manifolds coming from singularity theory. In the lecture of today, and also in the next one, we start to enter in the technical analytical core of the theory of Dubrovin-Frobenius manifolds. Whenever one develops a mathematical theory, the aim to which every mathematician should aim to is a classification of results, a theory of classifications of structures that we introduced by giving some axioms. Well, what I want to do in these two lectures is indeed to develop a classification theory for Frobenius manifolds. The way in which I will do this is by introducing some local invariants for these structures, which are complete invariants. That is, these invariants allow you to completely reconstruct the Frobenius structures. But before starting, I want to speak about this genericity condition. I will consider only the generic, so to say, Frobenius manifold. And so we can start to explain what I mean by this genericity condition. It is a semi-simplicity condition. So I want to start by speaking about semi-simple Frobenius algebras. So, again, I will consider K to be a field of characteristic 0. It's not necessary, but remember also that actually the case to which we will be mainly interested is actually K equals C. And in what follows, as usual, I consider an algebra A, which is associative, commutative, unital, an algebra over K, and furthermore, I also assume that such an algebra is of finite dimension over K. We have a following theorem. The following conditions are equivalent. Condition 1, there are no nilpotents in the algebra A, so are equivalent for the algebra A. So the first condition is there are no nilpotents in the algebra. The second condition is there exist vectors pi 1, pi n in A such that the product of pi I times pi j equals pi I times delta ij. That is, we have idempotents. The third condition is A is isomorphic as an algebra to the product of fields K times N. So this is a product of fields. In other words, multiplication is defined component-wise. And the last condition, number 4, there exists a vector E in A such that the operator of multiplication by the vector E, which is an operator from A to A, as a simple spectrum. If A satisfies one of the following equivalent conditions, we will say that the algebra A is semi-simple. Now, there are many ways to prove this result. I want to give a proof, a complete proof of this result, and there are many ways to prove it. But the proof I want to present today is based on a deep study of the structures of minimal ideals of the algebra. So, as the name suggests, the way in which I want to prove is study minimal ideals So, as the name suggests, what is a minimal ideal? It is an ideal who does not contain any other non-zero proper ideal. So, in other words, are minimal elements for the poset of ideals equipped with inclusion as an order relation. Well, we have an important remark. Minimal ideals are dual as a notion to the notion of maximal ideals. But there is a strong difference. Indeed, whenever you have a unitar ring, maximal ideals always exist. This is known as Krull theorem, and it is actually equivalent to the axiom of choice. But for minimal ideals, it is not at all true. So in general, in a ring, if R is a unital ring, minimal ideal do not exist. Example exercise. Convince yourself that in the ring of integers there is no minimal ideal. However, there is an obvious case in which minimal ideals exist. In particular, if R is a so-called Artenian ring. Artenian ring, so if R is Artenian, which means that whenever you have a chain, a descending chain of ideals, at some points this chain must stabilize. So if R is Artenian, then necessarily minimal ideals exist by Zorn lemma. That is again the axiom of choice. I claim that the algebras we are considering are obviously Artenian. So A is Artenian. And why it is so? Because the dimension of the algebra is finite. Indeed, notice the following. If you have an ideal of the algebra, then automatically it is a k-vector subspace of the algebra. So if you are considering a descending chain of ideals, you are considering a descending chain of vector subspaces in a finite dimensional space, then necessarily every chain stabilizes. So this follows from the fact that the dimension is finite, plus the fact that ideals are K subspaces. So this follows from this, the fact that A is Artenian. So we know that minimal ideals exist. Now I want to invoke an interesting result known as Brouwer lemma, which is a result which explains what is the structures of minimal ideals. Brouwer, let me say that Brouwer was one of the main mathematicians who started to study properties of Frobenius algebras. These algebras were introduced in papers of Frobenius. There is a fundamental work of Frobenius of 1903. But later it was Nakayama and Brouwer, and also a student of Brouwer who started again to study properties of Frobenius algebras. But let's go back to this Brouwer lemma. Brouwer lemma claims the following. If I is a minimal ideal of A, then we have two possibilities. Either I square equals 0, or I is the ideal generated by an idempotent element. By an idempotent element of the algebra A. How to prove this? We prove it as follows. Assume that I square is not 0. This means that there exist two elements, x and y, in the ideal, such that their product is non-zero. Then we can define the following morphism. A morphism of A modules. So we consider a morphism F from I to I. So I, being an ideal of A, is naturally equipped of an A module structure, and now I am going to define a morphism F from I to itself. And the morphism is defined as follows. F of A equals x times A. This is a non-zero morphism by assumption, and moreover, the kernel and the image of F are submodules of a domain and target space. But the fact that I is a minimal ideal is equivalent to say that there are no proper submodules inside. So by minimality, of I, we deduce that necessarily the kernel is trivial. And the image of F is I, so F is an isomorphism. But then that means that there exists an element E in I such that X equal X times E. But if now I multiply both sides by E, I obtain XE times equals X times E squared. That is, F of E equals F of E squared. But F is an isomorphism, so necessarily E equals E squared. And here you are an idempotent. How does idempotent arise? Finally, notice that the ideal E times A, so the ideal in A generated by E is non-zero, is a non-zero ideal. And again, by minimality of I, we deduce that I equals E times A. And this completes the proof of Brouwer lemma. Well, with such a tool, we are now ready to give a complete proof of this fundamental theorem. It is a theorem of structures of semi-simple algebras. So proof of a theorem well, there are some implications which are straightforward. For example, 3 implies 2 implies 1 is obvious. I prove that 1 implies 3. And I do that by induction on the dimension of the algebra. So if n is equal to 1, well, if n is equal to 1, A is a one-dimensional K-vector space, so is clearly isomorphic to K. And this is the content of point 3. So, inductive step, assume that it works for n, that the statement holds true for n minus 1. We want to prove it works for n. Well, we know that we have, by this remark, we know that A admits minimal ideals. By Brouwer lemma, we know that minimal ideal have the following form. I is generated by an idempotent of A. Then, so we have a minimal ideal I of a form E times A. Now, set I prime to be the ideal of A generated by 1 minus E. It is easy to see, so it is easy to see that indeed the algebra A is a direct sum of I and I prime. Moreover, I can quotient so that I can quotient, I can consider a quotient out by I obtain an algebra n minus 1 dimensional, which is without nilpotence, and then by inductive step the claim follows. So I prime is a n minus 1 dimensional K algebra without nilpotence, and consequently the result follows. So we have proved that this proves that 1 implies 3. By the way, by this argument, it is straightforward to see that the unit of A equals the sum of the idempotence by I. So what we still have to prove is implication 4. Well, I prove that 2 and 4 are equivalent. So one implication is straightforward. 2 implies 4. Just take E equals the sum of K times pi K, for example. And now let's prove that 4 implies 2. That 4 implies 2. So for this, let's do the following observation. By commutativity, it's straightforward to see that if we consider this family of operators, so we are considering the family of operator by multiplication by elements of A. By commutativity, it follows that this family of operators is a family of commuting operators. Is a family of commuting operators. So in particular, any operator of this form commutes with this operator, the operator of multiplication by E. But this implies that an arbitrary operator of this form preserves the eigenspaces. And in particular, it also proves that any operator of this kind is diagonalizable. But then it is a well-known result in linear algebra that whenever you have a family of commuting diagonalizable operators in a finite dimensional space, this family is simultaneously diagonalizable. So how to construct idempotence just by rescalings, common eigenvectors? I leave to you to complete the details. So simultaneously, so the family is simultaneously diagonalizable, and pi i's are constructed by rescaling, suitable rescalings of eigenvectors. Okay, we have introduced a notion, the notion of semisimple Frobenius algebras. We have many equivalent formulations for this notion, and now we can go to to semi-simple Frobenius manifolds. By the way, a remark, an interesting remark, important. Assume, you see, up to now, I never assumed the algebra to be Frobenius. It was just a commutative associative unital algebra. But assume corollary, assume that the algebra A is Frobenius. Then we have the following fact that, so we have a metric, the Frobenius metric, which makes A to be Frobenius, and we have that idempotents are pairwise orthogonal if I and J are different. That's obvious. It immediately follows by properties of idempotence and the Frobenius algebra property. So pi I equals pi I square, but the operator of by multiplication by pi I is self-adjoint with respect to eta. That is, this equals eta pi I, comma, pi I times pi j. But if I and j are different, then this is 0, and this gives you 0. So on Frobenius algebras, we have semi-simple Frobenius algebra. We have a basis of orthogonal idempotents. And as I said, as I already said before, the unit of the algebra equals the sum of its idempotents. But now I want to go to Frobenius manifolds. And in particular, I will introduce this class of Frobenius manifolds. It will be clear that what I mean by genericity condition. It is already clear by the fourth of the condition I wrote before. Maybe I keep this, but so why genericity condition? Well, because the fourth point was telling us that, you see, it's a very so to say, weak property, right? We are just assuming that there exists a vector, arbitrary vector in the algebra with simple spectrum. So definitely a generic condition. So now we are going from Frobenius algebra to important exercise. In the first of the lectures, I gave to you a list of Frobenius algebras. I warmly invite you to take each example and to try to understand which of that examples is semi-simple, and in case to find explicitly the idempotents, or to explicitly give nilpotents. In the next lecture, I will give the solution plus an interesting observation. But now I want to move on, and I want to speak about semi-simple Frobenius manifolds. So the way in which I introduced Frobenius manifolds was by saying that they can be conceived as family of Frobenius algebras. So it is not surprising, it is not a surprising definition the following. So here I am assuming that M, eta, C, E, and E is a Dubrovin-Frobenius manifold. I will say that the point P of M is semi-simple if the corresponding Frobenius algebra, which is defined on the tangent space to M at P, the metric is just given by the metric evaluated at the point, as well as the product and the unit, is semi-simple. So, from point 4 of a theorem, of a previous theorem, it is clear that the condition of semi-simplicity for points of a Frobenius manifold is an open property. That is, so remark, semi-simplicity is an open property. In other words, the set of semi-simple points is open. And why? Well, it follows from the previous theorem, point 4. To claim that P is a semi-simple point, it implies that we have a vector at P, the multiplication by which has a simple spectrum. But if we perturb a little bit by this operator, by deforming a little bit in an holomorphic way this tangent vector, we still have operators by multiplication by vector fields, holomorphic vector fields, which have a simple spectrum. So this implies that it is an open set. And actually, we have a following fact, that in the complex analytic category, the set, by the way, such a set, the set of semi-simple points, will be denoted by MSS. So we have the following fact, that in the complex analytic category, MSS not only is open, but it is dense. And we can also introduce the complement of this open dense subset, and such a set is the set of nilpotent points, so to say, points at which the Frobenius algebra have nilpotence, and this will be called the caustic. Of a Dubrovin-Frobenius manifold. In particular, one can prove that if the caustic is non-empty, then the codimension of the caustic is greater than 1. Greater or equal than 1. So, so this was a first fact. We also have a second fact, that if we are considering a semi-simple Frobenius manifolds, that is, Frobenius manifolds which admit at least one semi-simple point, we have in an open dense subset at each point some idempotent vectors. Well, it can be shown that these idempotents vectors, tangent vectors, can be locally glued together to give holomorphic local vector fields. I'm not claiming that in general you have a global section of a tangent bundle, but locally you can always consider them as local holomorphic vector fields. So fact 2, the idempotents define local holomorphic vector fields. By 1 by n, and these will be sections of a tangent sheaf.
Were you thinking that this was the one to obtain by parallel transport? Or?
Sorry?
If you start from a point and then you parallel transport these eigenpotents are still eigenpotents?
No. No, but I mean, I'm not saying that idempotents are flat, you see?
Okay.
You have these vector fields, but in general, a priori, there is no reason why these fields should be flat, you see? But still something, a sort of miracle holds true. We have a remarkable result. A remarkable result due to Dubrovin. It's a simple statement, which does not mean it is a trivial one. So we have this theorem by Dubrovin. The idempotent frame is holonomic. That is, so the idempotents vector fields define a holonomic system, holonomic frame. That is, they pairwise commute. They pairwise commute. I will prove in this lecture this theorem, but before giving a proof for the theorem, let me deduce immediately the following important corollary. The fact that the idempotent frame is an holonomic frame automatically implies the existence of a local holomorphic system of coordinates with respect to which pi I is a coordinated vector field. That is to say, there exists local holomorphic coordinates u1, un, such that if I consider the coordinate vector field attached to ui, this equals the idempotent vector pi I. This immediately follows from this condition. And let me notice that this is a very important point, because many formulas of a theory will simplify in this frame in these coordinates, in this system of coordinates. For example, it is now very easy to write down the components of a tensor C. So recall we have the tensor C, which is a section of what? Of these guys. So it is a tensor, a one-to tensor, which defines the structure constants of the Frobenius algebras at each point of the Frobenius manifolds. And we can write down the components of this tensor in this frame, in this system of coordinates. And because of this property, the components are particularly easy to write down. These are just a product of two Kronecker delta. These coordinates are so special that they deserve a name. We will call these coordinates canonical coordinates, or some people also call them Dubrovin canonical coordinates. Of course, canonical coordinates are not uniquely defined. Are not uniquely defined because we have two ambiguity in their definition. The first ambiguity is an ambiguity of permutations. Because, of course, we could choose a different labeling for the idempotent vector fields, and consequently a different labeling for the canonical coordinates. And also we have a shift ambiguity. Indeed, if I replace one of these coordinates by the same coordinate plus a constant, this condition is always the same. So, remark, we have two kinds of freedom. We have said differently, the canonical coordinates are well defined up to permutations and shifts. Up to permutations and shifts by constant. However, we have a canonical choice for canonical coordinates. And in particular, we have a following proposition. The content of the following proposition is that by using the only gadget that up to now I never invoked, that is the Euler vector field, I can fix once for all this at least the shift freedom. So canonical coordinates can be chosen so that the Euler vector field E equals the sum of Ui times the vector, the coordinate vector ui. As you will see in these lectures, I will implicitly use the following notational rule. For canonical coordinates, when I write down components of tensors, I will always use latent indices. And I will never use the Einstein summation rule. I will deserve the Einstein summation rules over Greek indices, which will be indices for components of tensors in the flat system of coordinates. Okay? Very good. Okay, I want to prove the following, that we can choose canonical coordinates in such a way that the components of the Euler vector field with respect to the idempotent vectors are just the canonical coordinates ui themselves. So how to prove this? How to prove this result? We prove as follows. I claim that it is sufficient to prove the following identity, that the Lie derivative along the Euler vector field E of the coordinate vector field d over d ui equals minus the same vector field. This for any I from 1 to n. Indeed, from this identity, we have the following. If, well, the Euler vector field will have some components which will be functions of the canonical coordinates times the ui. And if we are able to prove this, then it follows the following, that the derivative of the components ei with respect to duj is 0 if I is different from j. And the derivative of ei with respect to ui equals 1. So I leave to you, it's just a straightforward computation. From this, you deduce this. And from this, the claim follows. The claim follows. So we needed to prove this. And for this purpose, let me recall you one of the defining property of the Euler vector field. The Euler vector field is such that the Lie derivative of a tensor C equals exactly the tensor C. Well, but it is very easy to see that such a condition is equivalent to the following one. The Lie derivative of a product of two vector fields x and y minus the product of the Lie derivative of x times y minus the product of x times the Lie derivative of y equals the product of x and y, where x and y are arbitrary tangent vectors to the manifold itself. And why this is true? Well, this is obvious because you just need to use Leibniz property of Lie derivative and commutation with contraction of indices. But then I can specialize this formula. By taking capital X equal d over d ui, and capital Y equal d over d uj, with I different from j. And I deduce the following. I have Lie derivative of the I times the j plus the j times Lie derivative of the, the I times the derivative of the j equals 0, which means what? Which means the following, that, well, this is telling me that the Lie derivatives of the I times the j equals 0 whenever I is different from j. We deduce this from this, we deduce this. And but then what does it mean? That it means that this Lie derivative is orthogonal to all other idempotent vectors, and consequently this Lie derivative must be proportional to the I itself. So this means that Li di equals lambda I di for some lambda I, but then we need to compute this lambda I, and for that purpose, let me do it here. For that purpose, use again the same formula, but now take capital X equals capital Y equals the I, and you obtain the following. You obtain lambda I di minus twice lambda I di equals di. And from this, you immediately find that lambda I equals minus 1. And this completes the proof. Let me do a comment. If you consider the operator of multiplication by Euler vector field, from this result it is clear that the spectrum equals the canonical coordinates, the set of canonical coordinates ui. But according to point 4 of the theorem of the beginning of this lecture, it immediately follows the following, that if we fix canonical coordinates in this way, then all points, in this way, such that this is the expression for the Euler vector field, then all points at which canonical coordinates are pairwise distinct automatically are semisimple points. Automatically are semisimple points. So now I want to give a proof. Of this remarkable theorem of Dubrovin. But to that purpose, I need to introduce an extremely important tool in the theory. So I want to introduce the so-called extended deformed connection. So here I am always working on a given Dubrovin-Frobenius manifold, and now I am going to introduce an important character of a theory. So, as usual, M is a Dubrovin-Frobenius manifold, and I first introduced a family of connections called deformed connections. So, introduce the family it is a family of connections labeled by complex numbers, and these are connections defined on the tangent bundle of M, holomorphic tangent bundle of M. And I will define this connection by the following formula. I need to define this symbol. Well, I will denote as usual by nabla without upper index the Levi-Civita connection of eta. So this is Levi-Civita. And I will define this connection as a deformation of this vector field. So this connection is a deformation of the Levi-Civita connection, and the way in which I deform is by adding a scalar multiple of the product of the two vector fields. So here x and y are vector fields. In particular, D0 coincides with the Levi-Civita connection. We have a theorem. For any z, the connection nabla z is flat. Proof of a theorem. Well, whenever we have a connection defined on the tangent bundle, such a connection obviously induces connections on all the tensor algebras of a tangent bundle. So in particular, we also have a connection on the cotangent bundle. And as usual in differential geometry, I will denote this connection by the same symbol, nabla z. But if I have a section of a cotangent bundle of M, the system of flatness, the condition of nabla z flatness for Xi is the following differential, is the following system of the differential equations. So now what I'm doing is to consider a system of flat coordinates with respect to the Levi-Civita connection. As usual, we denote these by T alpha. And I am going to consider components of a given one form with respect to the T alpha. And now, what I am doing, I am going to write down what does it mean to be, for a one form, to be flat with respect to the connection nabla z. So this condition is equivalent to the following system of differential equations. So here, as I said, I am using Einstein's summation rule. And to claim that the connection is flat, it means that this joint system of differential equations is integrable. So for that we need to check what? I mean, obstruction to integrability is the following. We need to check that integrability we need to check if we take these double derivatives, they must give the same result. And so now what we need to do is just a computation. It's just a computation. We have the alpha, the epsilon xi beta equals the alpha, by using that equation, z c epsilon beta gamma xi gamma, which equals z the alpha c epsilon beta gamma xi gamma plus z square c epsilon beta gamma C delta alpha gamma C delta. And the epsilon, the alpha, C beta equals the same, in which we exchange alpha and epsilon. And in order the two are equals if the linear terms in Z coincides and the quadratic terms in Z coincides. But this means what? This means the following, that from the linear terms in Z, we are requiring that the alpha C gamma epsilon beta equals the epsilon C alpha beta gamma. And from quadratic terms in Z, we obtain the following constraint. C epsilon beta gamma times C alpha beta delta equals C alpha beta gamma C epsilon beta delta. But the first condition is telling us that the covariant derivative of C flat, that is, if we lower the index of C, such a tensor is completely symmetric in its four indices. But this was one of the axioms of Frobenius manifolds. And also the second constraint is nothing else than the associativity condition of a product. So, summary, each connection nabla Z is flat, and the reason is that the flatness condition is equivalent to these two conditions: complete symmetry of a tensor nabla C beta, C bemol, and associativity of a product. Well, with such a tool, I can now prove the theorem of Dubrovin. Holonomicity theorem. The proof. So, we have a following. So, to claim that to claim that this connection nabla z is flat identical in z means that the following operator equals 0. So we have a following. This operator for any choice of I and j equals 0. Then I apply this operator to pi L. By applying the operator to pi L, I obtain the following. Set, by the way, set the following. So as I said before, there is no reason for which idempotent vectors are flat, and I will call these the Christoffel symbols. I will call them gamma ijk. And I will also introduce structure constants for the commutator. Fijk. So using this notation, if I apply to pi L this operator, I obtain the following. Nabla z pi I sum over k gamma jlk pi k plus z times pi j delta lj nabla z pi j sum over k gamma il k pi k plus z times pi I delta li minus the sum over k and h of f ij to the power k gamma gamma k l h pi h plus minus z sum over k f I j k pi l delta k l. So I just applied this operator to pi l, and this must be equals to 0. Again, such an identity holds true identical in Z, and I can select the linear term in Z. So take the linear term in Z, and this gives you the following. If you do the computation, you obtain sum over k gamma jl k delta ki pi k plus sum over h gamma ij h pi h delta lj minus sum over k gamma ilk delta jk pi k plus minus sum over k sum over h gamma j I h pi h delta Li minus sum over k f I j k pi k delta KL, and this must be equals to 0. So I can, you see, each of these summands is a combination of these idempotent vector fields. I can just take the component with respect to one of them, to generic vector pi k, and I obtain the following identity. Gamma JLK delta KI plus gamma IJK delta LJ minus gamma ILK delta JK minus gamma JIK delta Li this equals Fij delta KL. So here there is no sum. Okay? I just took one component in this expression, and I have this. But if you set L equal to K, you see that this term cancels this. This term cancels this, and this term cancels this one. So let me use some colors. So if L equal K, I have that this cancels this, and this cancels this. And in particular, we deduce that Fijk equals 0. So the vector fields commute. Maybe it's better to stop for some minutes. Okay, so welcome back. Welcome back. So, okay, what we did right now was to introduce a family of connections, nabla Z, and we proved that that each element of this family is flat. Well, but actually, something stronger holds true. In particular, the following holds true. We can take such a family of connections and to rigidify it into a single connection, which will be the extended deformed connection, and it will turn out that this extended deformed connection is actually flat. So let me explain better what is going on. So, first of all, let me introduce some notations. Introduce two tensors. Capital U, calligraphic U, and mu, which are 1-1 tensors on the Frobenius manifold, so endomorphisms of a tangent bundle. And these tensors are defined as follows. U applied on a vector field X is defined to be just the product E times Euler vector field times X. Mu applied to the vector field X is defined as follows. You take 2 minus d over 2 times X minus the Levi-Civita connection, the Levi-Civita derivative of the Euler vector field along the vector X. So here d, small d, denotes the charge of the Frobenius manifold. That is, recall that we have a Killing conformal condition on the Euler vector field. D is the charge, and 2 minus d is exactly the coefficient of the Killing conformal conditions. And another working assumption that it is always it is a generic assumption that it works in all the concrete examples of interest, is that such an operator, which is again a 1-1 tensor, we assume that such an operator is diagonalizable. In particular, flat coordinates will be chosen so that the operator mu is diagonal, is in diagonal form. And in particular, we will have mu equals the diagonal matrix mu1, mu n, where mu alpha equals q alpha minus d over 2. I recall you from the first lecture on Frobenius manifolds that these coefficients q alpha appear in the following expression for the Euler vector field. So the Euler vector field was assumed to have the following form in flat coordinates. Is there any question? No. So here alpha from 1 to n. Okay, so up to now we introduced two tensor. This tensor is just the multiplication by Euler vector field, and this other tensor, which is assumed to be diagonal in flat coordinates, and in particular we have this form. And notice that also it is, these are just numbers, so it is a constant tensor with respect to the flat coordinates. Okay, with this, once we have introduced these two objects, calligraphic Q and mu, let me do the following construction. I consider the tangent bundle on M, and I consider the product C star M to M. And I can consider the pullback bundle on this product. So I will denote by T of M the tangent sheaf of M. As usual, P upper star Tm will be the sheaf of sections of the pullback tangent bundle. In other words, you can interpret section of this sheaf as vector fields on M whose components depend on a complex time Z. But we can also consider this sheaf, the inverse image of a tangent sheaf, which is the sheaf of sections of a pullback bundle which are constant along the fibers of pi. So, if a Dubrovin-Frobenius manifold is defined by the datum of many tensors on the tensorial algebra of a tangent bundle of M. But so we have a metric, Euler vector field, unit vector field, the product C. But what we can do is we can lift all these tensors to this pullback bundle, and I will denote by abuse of notation these lifts with the same letters. And moreover, I can also lift the Levi-Civita connection to this pullback bundle. So nabla is lifted to pi star Tn, so that the derivative along the z of y equals 0 for any section of an inverse image of a tangent sheaf. In other words, what I am doing is the following. I start from the Levi-Civita connection here, and I pull back it here. In such a pullback, I will do I consider the lift, the obvious lift, the derivative of of a vector whose components do not depend on z with respect to the vector field d over the z will be 0. And now I want to deform this lifted Levi-Civita connection. And for doing that, I needed to prescribe Christoffel symbols along tangential direction to n and Christoffel symbols along tangential direction to C star. So, as I said, what I want to do is to rigidify such a family. So, the Christoffel symbols along tangential direction to n will be exactly given by this formula. So, in other words, let me introduce a connection nabla hat. Actually, the connection I will introduce is a connection defined on a restriction on this pullback bundle to, here I already put C star, so okay, to P star Tm. So I want to define a connection on this pullback bundle, and as I said, I needed to define Christoffel symbols along tangential direction to m, and for that purpose, I will use exactly the formula we had before. But I also have to define Christoffel symbols along tangential direction to z, to this factor C star of this product. And this will be done as follows. So I consider the value of a lifted Levi-Civita connection along the z of y, and then I perturb it by adding the value of Euler vector field times y minus 1 over z, the value of the operator mu. This mu is sometimes also called grading operator, applied to the vector y, vector field y. So here x is a section of a tangent bundle of a tangent sheaf of m, and y is a section of the pullback sheaf of y. So we have the following theorem. Nabla hat is flat. And it is called the extended deformed connection of a Dobrovin-Frobenius manifold. More precisely, the flatness is equivalent to the following conditions. First condition is Nabla C flat to be completely symmetric covariant tensor. Associativity of a product the condition nabla of E equals 0 and the condition Lie derivative of C along E equals C. So as you can see, all these conditions are natural conditions defining. All of them arise either directly in the definition of the Dobrovin-Frobenius manifolds or are just an easy consequence, like this one. So, proof. So again, as before, the connection nabla hat induces a connection on the dual of this bundle. which is just the pullback of a dual tangent, of a cotangent bundle of M. And I can look for flat sections. So look for nabla hat flat sections. C sections of the pullback of a cotangent bundle of M. Well, we have this nabla hat flatness condition is equivalent to the following condition, to the following joint system of differential equations. What I am doing is just to write down in components okay, so what I did was the following. I consider a section of this bundle. Such a section admits the following as the following components. Xi equals Xi alpha, which will be functions of z and of t, flat coordinates on M, times the T alpha. This is the system of equations equivalent to the nabla hat flatness condition for Xi. To claim that nabla hat is flat, it means that this overdetermined system of differential equations is integrable. And again, what we need to do is to check integrability. So we need to do two checks. The first check is the alpha, the epsilon equal the epsilon, the alpha. And this is what we did before, right? When we proved the flatness condition for the family of deformed connections. And in particular, from this, we saw from the proof that it was equivalent to this condition, to the first two conditions. Symmetric and associativity. But we also need to prove the following. The alpha, the z, equals the z, the alpha. And let's do the computation here. Let's do this computation here. Maybe here. So this second condition holds true if and only if the following equation holds true identically in Z. 1 over Z, the epsilon mu sigma beta xi sigma plus open bracket C epsilon beta sigma minus C epsilon beta gamma mu gamma sigma minus the epsilon e alpha C alpha beta sigma minus E alpha the epsilon C alpha beta sigma plus mu beta lambda C epsilon lambda sigma, closed bracket, times C sigma plus a linear term in Z, which is given by C epsilon beta gamma times C alpha gamma sigma minus C alpha beta gamma C epsilon gamma sigma times E alpha C sigma equals 0. So we need to set equals 0. We need to check that this is 0 identical in Z. The linear term in Z is clearly 0 because this is associativity of a product. So this is 0 by associativity. From the definition of mu, we have the following. Recall that mu sigma beta equals 2 minus d over 2 delta sigma beta minus the beta is sigma. And this is 0 if and only if, so the epsilon mu sigma beta equals 0 is equivalent to say that the epsilon, the beta, epsilon sigma equals 0. That is to say that the Euler vector field is an affine vector field. Moreover, if we look at the terms with 0th power of Z, we have the following. We can expand. I can just replace this equation, which defines mu, here inside this term, and I obtain the following. C epsilon beta sigma minus 2 minus d over 2 C epsilon beta sigma plus C epsilon beta gamma d gamma e sigma minus d epsilon e alpha C alpha beta sigma minus E alpha d epsilon C alpha beta sigma plus 2 minus d over 2 C epsilon beta sigma minus d beta E lambda C epsilon lambda sigma equals 0. So we have this equation to be checked, and well, this cancels with this, and moreover, in this term we can use this property, the complete symmetry of this tensor, to replace it with E alpha d alpha C epsilon beta sigma. In other words, I can commute epsilon and alpha because of the completely symmetricity property of Nabla-C flat. And so by using also this property, I obtain the following. That this condition, the condition of being this size equals 0, is equivalent to the condition C epsilon beta sigma equals E alpha de alpha C epsilon beta sigma minus C epsilon beta gamma de gamma e sigma plus d epsilon e alpha C alpha beta sigma plus d beta e lambda C epsilon lambda sigma, but this is nothing else than the component of the Lie derivative of C along E, along the Euler vector field, is the component epsilon beta sigma. So we find the last condition, the Lie derivative of C along Euler vector field equals C. And this completes the proof of the flatness condition of Nabla hat. But let's summarize what we did. For semi-simple, well, we introduced the notion of semi-simple Frobenius manifolds. We introduced idempotent vector fields, canonical coordinates which are well defined because of a holonomicity property of idempotent vector fields. How to prove holonomicity? By introducing this gadget, this family of deformed connections. So it is a family of connections parametrized by C, but actually we did something more. We take this family and we rigidified it to a unique connection on this pullback bundle. And this rigidified connection is flat. Nabla hat is flat. So this means what? This means the following. At the end of the day, let me erase somewhere something here. At the end of the day, out of the blue, we are able to attach to a Frobenius manifold a joint system of differential equations of this form. So let me explain what is the notation now. So this system of equations is just this system of equations. But from now on, I will adopt a matricial notation. So now I will arrange C to be a column vector, even if it is in cotangent space. I want to work with column vectors. And so this now denotes this column vector. And C alpha denotes the matrix of operator by multiplication. So beta gamma, the entries beta gamma of this operator are just C alpha beta gamma. And U and mu are just the operators of multiplication by Euler vector field and this, and the grading operator. Notice, and now by transpose I means just transpose. I mean with capital T I will denote the transpose of a matrix. Remark. Important remark. As you can see here, there is a minus, here there is a plus. The point is that the operator U, I mean, there is always a transposition in the middle. The point is that the operator U is eta symmetric, is eta self-adjoint because of a Frobenius property. X times E, Y equals eta x u y. And for what concerns mu, I leave to you as a check, as an easy check, that mu is eta antisymmetric. That is to say, eta mu x y equals minus eta x mu y. This explains the reason why we have a different sign there. Okay, but let's summarize. From out of the blue, we are able to attach a joint system, integrable joint system of differential equations to a Frobenius manifold, and in particular, one of the components, one of the equations in this system can be interpreted as an ordinary differential equation in complex domains with rational coefficients, whose coefficients are depending on parameters. And what are these parameters? These parameters are the points of the Frobenius manifolds itself. So from now on, as I said at the beginning of this lecture, what I want to do is to introduce some local invariants for Frobenius manifolds. And for introducing these invariants, I will explicitly use this differential equation. Okay? So this equation can be interpreted as a family of ordinary differential equations in an abstract complex space C star whose deformation parameters are points of a Frobenius manifolds. So when I was asked to give such a course, I was asked also to present in a very summarized way basic results in the theory of ordinary differential equation in complex domains, and this is what I want to do now. I don't know how much time do I have? 5 minutes? Then no. For today, I think that it's better to stop. For today, I think it's better to stop. So let me explain what I will do next. I will try to summarize in a very short way basic results, introduce basic notions, and explain basic results in the theory of ordinary differential equations with meromorphic coefficients. And I will develop, I will introduce some tools which will allow me to define some numerical invariant by studying monodromy properties of solutions of these equations. Before, let me do the following simple remark. Simple remark here. We are working with equations of this kind. So ordinary differential equations in C star, and in particular we have and the coefficients depend on points of M. The point is that the coefficients are meromorphic. We have singularities of the coefficients. Singularities of the coefficients. Particularly, we have two singularities. All this will be, I am just anticipating things for the next lecture. We have a singularity at 0, and this will be called a Fuchsian singularity. But we also have a singularity at infinity, and this will be called an irregular singularity. So whenever you have a linear, it is a linear ODE, whenever you have a linear ordinary differential equations in the complex domains with meromorphic coefficients, it is a general fact, theorem, that solutions are in general multivalued, and you can show that they are well defined on the universal cover of the complement of the singularities of the coefficients. So this will be the starting point for the next lecture. I will start to present in a summarized way. I will try to be as much short as possible. And by studying monodromy of the solutions, this monodromy, what I mean by monodromy, I mean that I want to introduce a bunch of numbers, a bunch of matrices, which quantify how much multivalued solutions of equations are. But this will be the content of the next lecture. Okay, thank you very much.
Thank you very much.